Welcome back, all of you. Today we'll discuss about different types of signals that will be frequently used in signal systems and different types of communication system. So we'll begin with the first categorization, that is periodic and aperiodic signals. So periodic signals are basically those signals which repeats after a certain interval of time. That means we can say that x t plus capital T is equal to x of t. Such a signal x of t is known as a periodic signal, where the capital T is the period of this signal, period of xt. So we can say that the periodic signal xt remains unchanged when time shifted by one period. And for this reason, a periodic signal must start at time t is equal to 0. Always remember, a periodic signal starts at time t is equal to minus infinity. If it is started at some finite instant, let's say for example, if it started at time t is equal to 0, let us analyze the scenario when we are seeing that it's a periodic signal and it is starting at time t is equal to 0. Now see what will happen. The time shifted version of the signal will be what? X of t plus t, where capital T is the time period. So this is the time shifted version, and x of t is the original signal. It starts at time t is equal to 0. So we can say that the time shifted version, this time shifted version starts at time t is equal to minus of t, because we have already seen the transformation of signals. If we take a very simple example, let's say this is x of t, and if we time shift the signal by capital T, which is a positive quantity, the signal will become something like this. Now, are these two signals same? No, because the signal starts at time t is equal to 0. So it is always assumed that a periodic signal starts at time t is equal to infinity. This is the conventional definition of a periodic signal, that a signal which repeats itself after a certain interval of time, which is known as the period of that signal, time period of that signal, and it always starts from time t is equal to infinity. It should also be noted over here that no physical signals are actually periodic signals. No physical, or you can say practical real-time signals are periodic signals, since they all begin at some time or they cease to exist at a later point of time. No physical, or you can say practical or real-time signal are ideally periodic. The reason for that is because they start at certain instant of time. Instead of starting at time equals to minus infinity, they start at certain instant of time and they cease to exist at a later point of time. Similarly, we can also define the discrete time counterpart of the periodic signals. We can represent it like x of n plus n is equal to x of n. This is a discrete time periodic signal for all values of n, and capital N is the time period. It should be a positive integer. Now let us take a very simple example of periodic signals. Xt equal to xt is equal to e raised to power j omega naught t is a periodic signal. Let us prove this thing that this xt is equal to e raised to power j omega naught t is a periodic signal and its fundamental period is 2 pi by omega naught. This is the fundamental period is to be proved. And similarly, let us take the discrete time counterpart of it, e raised to power j omega naught n. We need to prove that this is a periodic signal and its fundamental period is again 2 pi by omega naught. It's a very important result which will be used in several examples. So let us prove this continuous time example first. We need to prove that xt is equal to e raised to power j omega naught t is a periodic signal with this 2 pi omega naught as the fundamental frequency, fundamental period. Fundamental time period is the smallest possible time period. So let us prove this thing first. We know by definition that a periodic signal can be defined as x of t is equal to x of t plus omega 1. Let us substitute the value of x of t over there. So it becomes e raised to power j omega naught t is equal to e raised to power j omega naught t plus t. Let us simplify it with omega naught t into e raised to power j omega naught to t raised to j omega naught. Now, in order to prove this equation, this e raised to power j omega naught t should be a unity. It should have a unity value in order to prove this equation, right? So from this equation, we can say that e raised to power j omega naught t is equal to 1, or we can say that e raised to power j 2m pi is equal to 1. This e raised to power j omega naught t can be written as e raised to power j 2 pi 2m pi, because omega naught we know is equal to 2 pi m by t, where m is any positive integer. Alright. So now let us compare the power of exponents. So you can say that omega naught t is equal to 2 pi of 2 pi m. Thus you can say t is equal to 2 pi m by omega naught, and the fundamental time period for the fundamental time period m, the value of m will be 1, which is the fundamental period is the smallest positive value. So time period is equal to 2 pi by omega naught. Always remember, for a complex exponential like e raised to power j omega naught t, the fundamental period is 2 pi by omega naught. It's a very important result. Always remember this. Similarly, you can prove the discrete time counterpart of this. Another important result regarding the periodic signal is that suppose we have a signal x of t. Rather, let's name this concept as sum of periodic signals. Let us say we have a signal x of t, which is equal to sum of n number of periodic signals x1 t plus x2 t plus x of n. All these signals are periodic in nature. Periodic signals with fundamental period t1, t2, tn. Okay. So xt is a signal which is sum of n periodic signals with fundamental periods t1, t2, t of n. So we can say that this xt will be periodic if and only if the ratio of any two periods is a rational number. So very important result. You can say that xt is a periodic signal if and only if ratio of any two period is a rational number. Rational number is you can say ratio of integers. And the fundamental period of xt is equal to LCM of numerator of t1, t2, tn divided by HCF of denominator of t1, t2, tn. Always true. If you are given a combination of signals, first you can check whether it's periodic signal or not by satisfying this condition, and if it is periodic, then we can find its fundamental period using this expression. Let us do some example based on this. Just a very basic example. Let's say we have a signal x1t, whose fundamental period is t1, that is equal to 5/7. x2t is another signal, any other periodic signal whose fundamental period is t2, that is equal to 3/2. So first of all, we find out whether it is a periodic, another signal x of t, which is sum of x1t plus x2t. We need to find out xt, whether this xt is a periodic signal. If yes, what is its fundamental period? To check whether this xt is a periodic signal, we need to satisfy this condition. The ratio of the period should be any two periods. Here we have only two periods, so the ratio should be a rational number. So you can see t1 by t2, or t2 by t1. You can see it's a rational number. So we can say that xt is periodic. Now let us find out the period of xt using this expression. So the period of xt can be t, that will be equal to LCM of the numerator of two time periods. That means LCM of t1, t2 divided by LCM of numerator of t1, t2, HCF of denominator of t1, t2. So numerators are 5 and 3. What will be its LCM? Its LCM would be LCM of 5, 3 divided by HCF of 7, 2. So result into LCM of 5, 3 will be 15, and HCF of 7 and 2 will be 1. So the equivalent time period of xt comes out to be 50. One important result, we have already seen that the fundamental period of a complex exponential is 2 pi by omega naught. Similarly, the fundamental period of sinusoidal signal is also 2 pi by omega naught. Always remember these relationships, they're very important. Alright, so now based on the above concepts, let us do some practice over this periodic signals. So first one is x of t is equal to cos of t. What will be its fundamental period? It's a sinusoidal signal. So for sinusoidal signal, the fundamental period is usually time t is equal to 2 pi by omega naught. Here omega naught is equal to 1, so you can say the time period here is 2 pi for this. space. Second one is xt is equal to cos 2 pi t. Again, we know it's sinusoidal signal. So this is the fundamental period 2 pi by omega naught. And 2 pi here is, sorry, omega naught over here in the signal is 2 pi. Time period is 2 pi by omega naught. And omega naught is 2 pi, so it effectively becomes 1. So the third one, similar to the time period, will be pi by 2. Fourth one, now it's a combination of two periodic signals. Cos pi t is a periodic signal. Similarly, cos 2 pi t is a periodic signal. And the fundamental period of this, let me say it's a periodic signal, t1 is equal to 2 and t2 is equal to 1. The fundamental period of cos pi t is 2 and fundamental period of cos 2 pi t is 1. So the effective time period will be what? First of all, you need to check whether the sum of these two is a periodic signal or not. You can do that by taking the ratio of T1 and T2. You can take the ratio of T1 and T2. If it comes out to be a rational quantity, you can say that the summation is also a periodic signal. In this case, it's a rational. So you can say this summation cos pi t plus cos 2 pi t is also a periodic signal. And its period is LCM of numerator divided by LCM of the denominators of the time periods. So the overall time period will be 2 by 1, which is 2. Next question, fifth, it is similar kind of question. Sin 2 pi t and sin t. The individual time periods would be t1 is equal to 1 and t2 is equal to 2 pi. Now we need to check whether the summation of these two is a periodic signal or not. We'll take the ratio of t1 to t2, 1 upon 2 pi. 1 upon 2 pi is not a rational quantity. Hence, we can say that this fifth question, that is summation of sin 2 pi t plus sin t, is a aperiodic signal. Moving on, the sixth part. In this question, it is 1 plus sin 2 pi t. That means a constant value is added to a sinusoidal signal. If we look at it graphically, we add a constant value to a sinusoidal signal, or something like this. The overall graph shift upwards, right? But the period or the periodicity is not affected at all when we are adding a constant value to a sinusoidal signal. So we can say that the overall signal xt, which is 1 plus sin 2 pi t, is again a periodic signal with period that of the sin 2 pi t. The period will remain same, that is the period of sin 2 pi t. Addition of a constant value does not change the periodicity. It is just shifting the waveform upward or downward. So the periodicity is not affected. So period will remain same, that is the period of sin 2 pi t. So its fundamental period will be the period of sin 2 pi t, which is 1. Alright. Moving on to the seventh part, which is cos t plus sin root 2t. Solve this one now. Seventh one is xt is equal to cos t plus sin root 2t. It is again a combination of two periodic signals. Now let's find out the individual periods. t1 is equal to 2 pi, that is the period of cos t, and t2 is equal to 2 pi by root 2, that is the period of sin root 2t. And now let us check whether this combination, this plus this, is periodic signal or not. We'll take the ratio of t1 to t2 or t2 by t1, and we find that it's t1 by t2 equal to what? It's equal to root 2, right? Which is not a rational quantity. Hence, we can say that the signal xt is a aperiodic signal. Thus, we need not find its fundamental period because it does not exist. Now, the eighth part is which was xt is equal to 2 cos 20 plus 1 minus sine of 40 minus 1. Is again a combination of two sinusoidal signals. So we will find out the individual periods first. T1 is the period of this 2 cos 20 plus 1. For a sinusoidal signal, we have already seen that the fundamental period is 2 pi by omega naught. Omega naught over here is 10. So it will be 2 pi by 10. That comes out to pi by 5. Similarly, T2, time period of sine 40 minus 1 will be 2 pi by 4. So omega naught over here is 4. So it comes out to be pi by 2. Now the next thing is to find out whether this combination is a periodic signal or not. So we'll find out the ratio T1 by T2 or vice versa. And to simplify it, it comes out to be 2 by 5, which is a rational number. It's a rational number. So you can see that xt is a periodic signal. Now we move on to find out its fundamental period t, which is LCM of, you can say, the numerator of t1 t2, that is numerator is c 5 comma 5 divided by HCF of the denominator, that is 5 comma 2, and it comes out to be 5 by 1 or 5. This is the fundamental period. The 10th part is xt is equal to e raised to power plus minus j omega naught t. We've already seen that that it's a periodic signal. Every complex exponential signal is a periodic signal, and its fundamental period t is equal to pi by omega naught. We will not use that again. Next part is xt equal exponential, and the argument is j times pi by 2 t minus 1. We need to find out its fundamental period. So it's a complex exponential. Clearly we can see that it's a complex exponential. So the fundamental period will be 2 pi by omega naught. That's the value of omega naught, that is. So the value of omega naught is pi by 2. So clearly we can see that the time period comes out to be 4. Moving on to the next. Xt is equal to e to the power minus 1 plus g times of t. This is the 12th part. So again you can say that it's a it's a complex exponential. So you can see that it's this kind of a signal, e to the power minus t. If we simplify it into e to the power minus g. To simplify this question, we get two terms, multiplication of two terms, that is e raised to the power minus t into e raised to the power minus j times of t. Now we know that this is a aperiodic signal and this is a periodic signal. This is a aperiodic signal and this is a periodic signal. So the overall result will be a aperiodic signal. Another important result from this example, multiplication of a periodic signal with a periodic signal results into a periodic signal. On this remember this result. And the last question, 13th question, is xt is equal to sine square of t. We need to find out its fundamental period. Let us simplify this question a bit first. 1 minus cos t by 2 then divided as this, and further it will be written as 1 by 2 minus 1 by 2 times of cos of t. Overall it's a sinusoidal signal, and thus a constant value is added to it. We've already seen a similar kind of question before. that on addition of the constant value in the sinusoidal signal does not change the periodicity of the signal. It only shifts the signal upwards or downwards. So here we are concerned about only the periodicity of the signal. Fundamental period will be the period of the sinusoid. So the overall period will be period of cos 2t. That will be 2 pi by omega naught, and omega naught over here is 2. The overall time period is pi. So that is all in this video. You can practice similar kind of questions from the books that I have already mentioned to you. And in the next coming lectures, we'll discuss further different types of signals like exponential signals, energy signals, power signals, different commonly encountered signals like signal functions, order functions. So these kind of signals will be discussed in the